Okay, well, hello everyone. Thank you for joining us for the very final seminar of the semester. So this presentation will be recorded and you can watch most of our past seminars on our YouTube channel by searching MIG's seminar, so be sure to check that out. Before we begin, we want to provide a land acknowledgement. We respectfully acknowledge the land in which we gather as the ancestral homelands of the Beothuk and the island of Newfoundland as the unceded traditional territory of the Beothuk and Mi'kmaq. We would also like to recognize the Inuit of Nunatsiavut and Nunatuavut and the Innu of Nitassinan and their ancestors as original peoples of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. So today we will hear from Dr. Neil Bose. Dr. Bose was appointed President and Vice-Chancellor pro tempore on April 6, 2023. He served as interim provost from September 1st, 2022. And prior to this, Dr. Bose was Memorial's Vice President of Research from 2017 to 2022. Dr. Bose was principal of the Australian Maritime College, the National Institute for Maritime Education, Training, Research, and Consultancy at the University of Tasmania between 2012 and 2017. Before his move to Tasmania, Dr. Bose was a long-standing and respected member of Memorial University's research community. He came to Memorial in May 1987 as an assistant professor in the Naval Architectural Engineering program. In his time at Memorial, Dr. Bose served as director of the Ocean Engineering Research Center, chair of the Ocean and Naval Architectural Engineering program, and in 2003 was named a Tier 1 Canada Research Chair in Offshore and Underwater Vehicles Design in the Faculty of Engineering and Applied Science. He received the President's Award for Outstanding Research in 1992. An internationally respected researcher, Dr. Bose received an honorary degree from the Nikola Yaptsarov Naval Academy, which is the oldest technical educational institution in Bulgaria, on October 8, 2017. Dr. Bose obtained his Bachelor of Science in Naval Architecture and Ocean Engineering from the University of Glasgow in 1978, and his PhD also from Glasgow in 1982. As a researcher, Dr. Bose's interests include marine propulsion, autonomous underwater vehicles, and ocean environmental monitoring. So with that, I will now pass it off to Dr. Bose.
Thank you. Welcome everyone, and thank you for coming and listening to me, and I hope you enjoy what I have to say. It's a bit different for me talking about research because I spend all my time doing admin stuff and chairing meetings and things. So let's see how this goes. It's a long time since I've done this. So I'm going to be talking about work that we've done over the last 3 or more years, actually, because it's been funded over a series of projects. But this particular project is linked with testing an AUV in an adaptive mission, and the work was done in Baffin Bay, and I'll explain why it was done in Baffin Bay as we go through this. The presentation was developed primarily by my postdoc, who was previously a research student, a PhD student, Jimin Hwang, and she was a PhD student at the Australian Maritime College that Rachel just referred to. So she finished there and then joined here as a postdoc, but she works remotely. So this is the team of the people, research team that went to Baffin Bay. Behind is the AUV. This is Memorial's Explorer AUV, which lives quite a lot of the time out at the launch in Holyrood and MI facility. And I work closely with Marine Institute and really happy to be working at the launch because it's a perfect place to do a lot of prep missions for this type of work. So this is the team. We have Dr. Shi Chen, who got a PhD last July and came on this mission as the last thing she did with us. and now works for an organisation called TCOMS, Technical Centre for Offshore and Marine Systems or something, in the National University of Singapore as some kind of postdoc. Me, of course, Dr. Jimin Hwang, who works still with us remotely from Australia. Ms. Janelle Nazareth, who's just handed in a master's thesis on part of this work. Gina Miller, who was the AUV operator, but has been poached by the National Research Council and paid more. So she works down the hill in the facility there. And Craig Bolger, who many of you probably know because he's actually instructor here in the School of Ocean Technology and is also a master's student, sort of halfway through, maybe a bit more than halfway through his master's program. So underwater challenges, many of you will know this. When you go into the ocean, there's severe pressure, you don't have GPS, there are unknown currents, and communication is extremely limited, and that limits how we do missions. This project was focused on a target of interest being mixed phase oil plumes, and it had followed through a series of different projects that had been funded first by DFO, then in this case for the mission in Baffin Bay through NSERC, through the Alliance programme. So we had put in place various pieces of work around detection. You can't use just one sensor in the ocean to detect oil or methane gas, so you have to use a variety of sensors. So we build a modular structure as to different sensors, and the work that we have done has focused on making the AUV more intelligent, so that most AUVs, commercial AUVs like the one that we used, you pre-program, it goes off and does the mission, records data, and you take the data off the vehicle at the end of a mission, download it, do your analysis. What our focus of the work was to get that analysis done in real time on board the vehicle and make changes to what the vehicle was doing on the fly and have an improved mission or a more substantive mission because of that. So, and that's what we were really aiming to do. So how do we achieve that? Well, here's the AUV itself. The AUV, as you could tell from the previous picture, because there were people in it, it's about 5.5 meters long, and it was built by International Submarine Engineering. It's one of their Explorer class of AUVs, and it was number 2 that they built. So number 1 went to Ifremer in the south of France. Number 2 was bought by us. In 2005, was delivered here in 2006. I was still here at that time. It was before I went to Australia, and I was the principal investigator who tried to get the money to build this thing and only got half the money. So when it was delivered to us, it was stripped out, had very little battery, didn't have a inertial navigation system, and all sorts of things it didn't have. And during the course I was away, a group of other people here, including Ron Lewis, managed to get more money and fix all that stuff up. And so it's a much better vehicle now than it was when it was bought. And you can, this picture is the pressure vessel open. You can see the masses of electronics that are inside, which we spent rather a lot of time, more than we wanted to, delving into when we were on the ship in Baffin. This slide gives a sort of modular idea of what, this mouse has a cable on it. I think you can see my mouse. So So inside of here, we put in various sensors. The primary ones was a scanning sonar on the top here. And we have two fluorometers that were measuring the amount of hydrocarbon, certain types of hydrocarbon in the water. We also have up at the top a set of 8 100 milliliter water samples that can be triggered by the systems on board. So inside of the vehicle, most of it is flooded, obviously not where the electronics is. So there's a centerpiece in the middle, which is a pressure vessel. This vessel is rated to 3,000 meters. I wish it could dive to 3,000 meters, but we had some problems with that. And most of the instruments are set up either in the flooded fore section or the aft section. As you can see, we put a set of them on top of the vehicle because we wanted them out in the flood. So we have the forward payload section, we've got the aft payload section, and there's a whole load of stuff on there as well, which is part of the vehicle operation. So the vehicle is controlled by its vehicle control computer, which we refer to as the front seat drive computer. We have a back seat drive computer, and it's set up in the same way as, you know, you have this person in the back of your car and they say, go here, go there. No, not there, go there. So that's essentially what we set up, a backseat drive computer. And the front seat drive computer runs International Submarine Engineering's ACE control system, which is operating the vehicle. Backseat drive computer is taking data from the different sensors, the sonar, the fluorometer, and analyzing it and pushing out instructions to the front seat drive computer. Yeah, I really do want you to go there, you know, that sort of command. So getting that all to work has been the focus of our research team for about 4 years. And hasn't exactly been straightforward. There's been a lot of work ongoing, and different people have done different parts. We've used, you see this term MOOSE, and the MOOSE IVP software is a MIT-based open source software designed for running autonomous underwater vehicles, and you can use that, and you can also build subroutines. So all of those 5 P waypoint, P plume, P prob, etc., are all subroutines we've written over the years to add to the shell of the MOOSE. So we're making control decisions in that backseat drive computer, telling the front seat drive what to do. So that's front seat drive, that's back seat drive. I should say I've simplified Jimin's presentation quite a lot to get rid of all of animations, because it makes it easier for me, but if you want the full version, you have to ask her to present it. So what we have set up is a search phase, a course search over a large region. So we go to a given waypoint, we do a bow tie type circling, and our sonar is taking data the whole time. And we preset the waypoints. We can actually design the waypoints from the backseat drive if we wanted to, but in the mission here, we actually preset them. So it goes off to waypoints, does these bow ties, takes in a lot of data, analyzes that data, goes back to where it thinks there's a point of interest that it's decided, the backseat drive computer has decided, has an area of interest, goes back, does a survey. Does a survey where it does a detailed investigation using, in this case, the fluorometer, analyzes that data for a potential high spot, and then goes down back to the high spot completely autonomously and takes a water sample. So there's a number of operational and safety issues involved. Obviously, if the backseat drive computer is telling the vehicle where it can go, well, you need some fail-safes, because if the backseat drive computer autonomously makes a mistake and says you're operating, say in Baffin, it says go to the UK, you've got a problem. So for the front seat drive computer has some limits. It says, hold on, no, we're not going there. Actually, we set a box, basically, a 3D box. And if it goes outside of that, mission aborts. So shut up to the backseat drive. So how do we test it? We do initially, all of the runs are done in simulation. And once we've done the simulation, we then can get out into the field. So here's an example of data that actually, this data comes from the Holyrood Arm, and these are sonar responses that we picked up in the arm. Some of you may have known we were using air bubbles to simulate things in the water. We had a big pump pushing out air into the arm. So these are sonar records of bubbles, we think anyway. Here's a set of bubbles. So what happens is that's the raw data, and through a series of analysis steps, which I don't want to get into, probably can't, in fact, because you'd have to have the student here to tell you how this was done. This was Janelle's work, incidentally. We identify certain areas set up in these rings that are areas of interest. We were particularly interested in natural seeps in this work rather than oil spills. Previous work had been on oil spills, clouds of oil in the water. This was on natural seeps. And so what we expected is columns of oil and methane coming up from the seabed. So we were looking for sort of focuses in the water of this type of stuff. So that was the basis of this analysis. After the sonar data is done, as I said, we're also running a fluorometer, and this is data from the fluorometer, and you have the track data as shown in the left-hand slide here, and along the track you have a high spot. So, but that may or may not be the high spot for the region. So through a series of analysis, one postulates what the rest of the data looks like in areas that you actually haven't taken measurements. And so through a long track, this red circle shows the high spot, which is the survey part of our analysis. Remember, the analysis done in real time on the machine, on the vehicle. So it's identifying a high spot, which it can then go back to and take a water sample. So that's a survey phase. So we wanted to test this in the ocean. We wanted to use real oil and gas, but we can't go about throwing oil in the water without a lot of environmental assessments and so on. There is actually a project based in the Marine Institute. Rob Brown in part of the Marine Institute is trying to work through a DFO funded project that does actually put oil in the water, but it's been years and it still hasn't been given the go ahead. So what we thought we would do is use a natural oil seep. The clouds of oil, as I said, takes a different form. There's a region of natural oil seeps. It's the biggest region in Canada. It's been there for, that we know, tens of years and possibly hundreds of years, actually, off Scott Inlet on the northeast side of Baffin Island. And so the region is actually all over this area, but the areas that we focused in to do our work were primarily the area 2 here. So 2 is where we knew from previous work done, seeps were actually seen at seabed at about 270 odd meters deep, 250 odd meters deep. Bad weather comes along though, and so you can't spend all the time, especially in the ship we were in, offshore. So we actually had to shelter inside of Scott Inlet for quite a lot of the days we were there. And also because we had quite a lot of trouble with the AUV. And so we did missions in the area which is designated as 1 here. So as you can see from the latitude here, 70, 71 degrees north. So the first area where we did a lot of prep work was in the fjord here. It's a very deep fjord, about 600 meters deep. Water's crystal clear in the fjord. After a snowstorm, wasn't so crystal clear in the area of the anchorage. So we used this refuge harbour area to anchor down in here where the anchor is, and did a lot of maintenance work on the AUV. We then moved offshore to the area of the seep, and you can see there's a deep canyon from the contours on the chart from the fjord, which is glaciated and cleaned out the canyon out into the deep ocean further offshore. So these are just a list of papers of all those people who've seen or documented oil in this region, oil and gas, and you can see all around that region, and in fact, northwards towards Pond Inlet and so on, there are oil seeps there. And if you talk, as I have done, to people in the area, because we actually, what I haven't said in a lot of detail in this presentation, but we worked with the people of Clyde River to make sure that they were okay with us doing this mission. We had to go through a Nunavut Impact Review Board assessment and get a permit from the Nunavut Research Institute before doing this mission. But when I talked with people in Clyde River, they were well aware that there was this oil in the region, and they'd known about it for years and years and years, of course, so of interest. So here, this is the vessel we use. We spent a lot of time selecting the vessel. It was actually quite difficult to find the right vessel, partly because when we did the costing for the project, we thought things could be done more cheaply than they resulted. And this turned out to be the most reasonable vessel. Actually, I think some of you may know that a Nunavut research vessel winters at, or has wintered at Holyrood. That's about a 65-foot length vessel. The cost of that to charter is the same as this one. This is a much bigger vessel from the Greenland Institute of Natural Resources. So this vessel was lovely, has a really low aft deck, which was perfect for our operation. And the red area is the area we commandeered for the lab work, and the area below, the deck below, was our accommodation. The AUV was affixed to the afterdeck. So we had all of the aluminum structure is a brand new launch and recovery system, which we had built in technical services this time last year. Took about 6 months, and worked perfectly actually for the mission. Was based on a previous design. for the same type of vehicle that was modified to all fit. Question? Ah,
How you access it.
I have no idea.
We could wait to do questions.
Yeah, let's do wait, because otherwise I won't finish, and then, yeah, anyway. Oh,
We have to double check that there's nothing wrong with,
yeah, are they,
just in case
maybe,
this is an issue. Sorry, just 1 second.
second.
Okay. Okay, so just at the end of the presentation, not,
cool.
not to worry.
Mm-hmm.
We'll just continue with that.
I'll have to make sure this time.
Yeah, perfect.
Okay. Yep. Good. Yeah, so this launch and recovery system was built by Tech Services and was modified so that the whole of the AUV and the launch and recovery system would fit in one 20-foot container, which for shipping, because we had to ship it from here to Nuuk to be fastened on the ship. It's actually welded to the deck for the mission and cut off afterwards. So to launch, how this worked is it's sitting on the deck. The A-frame is used as the crane, and it has its own chain drive that drives the ramp out, as you can see. And then the slider part lowers down, and when you get it to a certain point, you pull a release pin, and it launches the AUV down into the water, and off it goes. Your ship should be moving slowly ahead, about 2 knots when you do that. Launching it is easier than picking it up. So especially, and so the big challenge, in fact, most of the time we were there, except doing our operations in the fjord. In the fjord, it was often quite windy, but when we were very lucky, when we were offshore, it was actually fairly calm. But if there are any level of waves, that's when the problem arises. You can't do this in huge waves, and so you'd have to recover. So the recovery, and you can see how flat calm it is here, but the AUV has a pop-up buoy that is released from the front of the AUV. That yellow thing that looks like a football, it's actually a circular part of the hull, has been popped out, and this line is released, and then the line is picked up, brought on board, and then the AUV is winched in. So there's a winch on the front end of here, and so it's being winched in. The ship's moving slowly forwards, and as it comes towards the ramp, it's winched up the ramp and then is picked up. This is quite a long video, so but I'll let it play for a bit, and then I might speed it up as we go through. But as you can see, it's fairly critical to avoid the AUV hitting something and damaging itself. Took a chunk out of the front of the AUV at first, and I had to make a very small modification to the roller system. So here you can see how the ramp is winched up, and the two are aligned, and it's winched up, and then where are we here? And this filming, incidentally, is probably recovery. We probably did this 50 times when. So it got to the point where it got quite smooth by the time the first time we were dead nervous, of course. Brand new system. Let's speed this up a bit. You can see, yeah, so it's again winched up by the A-frame, and the chain drive pulls the sliding part in over the stern, and it's because of all the heights, and you have to sort of play around a little bit with the crane stuff, and in concert with the slider part. So that's how it all works on a good day. And we actually had very little problem with this, but as you can see, most of the time it wasn't too windy. Incidentally, this video I think is yeah, it is. You can tell from the watercolor. This is actually in the field where we were did our test, a lot of the tests. So let's move on to results that we got. So we had a lot of maintenance issues with the AUV. This AUV is now 18 years old, and even though we've been using it at Holyrood, the first time we actually launched it in Greenland before we motored over to Baffin Bay. We got a fault which Gina had never seen before, of course, right? So that fault actually dogged us the whole time we were in Greenland, in Baffin. It was a water fault alarm on the propulsion motor. And there'd been water fault alarms on the fins, the planes that are controlling, but there's 6 of them. If one of them is a problem, you can sort of get around it, but you can't get around the one on the motor. So so it came, then it disappeared, and we think, okay, and then it came back, and it did this the whole time, and we eventually had to do a lot of extreme maintenance, taking the whole pressure hull apart and tracking through and unwiring it, and taking apart the connectors and putting them back together. And even on our last mission that we did, it faulted, and we just packed up at that point. But so we did 6 missions. And this is a smattering of those missions and what they did. So, so as I explained, we tested the different subroutine mission files separately first. And I said that we had set it up to do a bow tie, and that bow tie also, vehicle also did a bow tie when it was sent back. Planned to do a bow tie, went set back to take a sample, was supposed to do a bow tie while the 8 samplers are set off. So you're in more or less the same region. So this is our mission of this particular, testing the sampling, the bow tie shape, and then this green thing is the sample. We tested our survey, you know, fairly normal lawnmower type survey. We tested our search phase and survey with our bow ties at each waypoint. The reality is, if the vehicle behaves, it doesn't quite follow. You don't get a nice smooth bow tie because of the way it's being driven. The bow tie is actually driven by the backseat drive computer. So it's saying this course, this course, this course. So it's actually an octagon type thing. And so this is sample 1, the sampler operation, and as soon as we've taken a sample, we have to recover because we have to offload those samples into Niskin bottles so that we've collected them. This is the lawnmower path. This is the search phase path. Most of these missions were done in the fjord. And there's a long story as to why we were in the fjord, partly weather-based, but partly because we had a couple of days, we just had the thing in bits completely. Then we went actually the first one here was still in the fjord. We tested a mission where we did a series of waypoints with searches. After the mission, the analysis done on the backseat drive computer. So this was the go out, do the survey, finish your survey. In this little curve here, the vehicle has done its analysis. Actually takes only, even though there's a lot of analysis needed, it only takes a few seconds. So that few seconds, it's worked out that the high spot is here. So it's turned around, come back to the high spot, done its bow tie shape again, and taken a water sample. So we then went offshore where the seats were expected to be, and we did a mission. This zigzag is over the area where we knew the seats were supposed to be. Because of the problem we had with the maintenance issue, the leak, we ran at fairly low, shallow, not deep down, and we didn't see anything in the water. We were wanting to see these columns of methane and oil. We never saw anything. So, and I should say this is now the last day after 2 weeks, and it's calm, and we've got like a window until 4 p.m. and then the weather's going to change and all. The usual thing when you go offshore. So we've got this mission. We did. So we put everything into a last mission and sent it down to 200 meters, and we shortened the mission. So this is part of the same zigzag. We set it off on the search, survey, and then sample mission. As you can see, well, if you probably can see here, that it finishes its mission and then does the analysis, finds a high spot, and it was about to take its sample when we got a water alarm in the pressure hull, which the last thing you want to have is water in the pressure hull, right? Yeah. So, but we had thought that what would happen if we had to abort too soon. So we had a line in our code that said, just take a sample. So, and although you can't communicate lots and lots of information backwards and forwards, you can communicate abort. You can communicate go to line X in the code. So we sent a go to line X in the code, take a sample and abort mission because we'd got this water alarm, right? So so that's what happened. It took a sample, it came back, we hauled it on board, we took the water sample out, and we that was our weather window. We had to return back to charter window and weather window. We had to return to Greenland. So when we did eventually take the vehicle to bits, there wasn't any water in the pressure hull. I was actually expecting a bucket of water in the pressure hull. It came up. Of course, the worry you've got is you've got water in the pressure hull. It's leaking, so it's going to sink, and you lose the vehicle. There was one point on this mission, I should say, where I wouldn't have been too unhappy to have never seen that vehicle again. But it came back, and there was no water in the pressure hull. But because we'd been working on the vehicle inside of in very difficult conditions, a little piece of metal had fallen into the water alarm and shorted the water alarm. So and that's how sensitive some of the stuff is. But we did have a fault on the same connector, which I talked about, that had dogged us all the way through, and that still is an issue that needs fixing. Hasn't quite. We'd been waiting for parts after we came back. So that's more or less where we are, and I think lessons learned, future directions. We published a paper of what we did do, which is important for our funding and for ourselves, of course. That just came out on the 1st of February. And it was funded by, this mission to Baffin was primarily funded by NSERC. So maybe I should go back and leave that picture up, or maybe we need to get online and see what's online. Yes. Okay, so that's it. I'm very happy to answer questions, or try to.
Great. Thanks so much, Dr. Bose. That was fantastic. And as mentioned by him, if anyone has any questions, now is the time. And if anyone online has questions, you can either put it in the chat or raise your hand and I'll be able to unmute you. Anyone here? Okay.
I was on a National Research Defense ship, and the computers that we had on board for analyzing data were the size of refrigerators. Was that something that y'all were using as well, like these big computers that analyze the data? Or did you have something smaller and tidier?
So you saw in the picture all of the electronics inside. That's a 19-inch rack that slides in and out, but that has everything on it for the machine, for the AUV. The vehicle control computer is about a little cube, about 100 millimeters edge, right? And I'm not sure exactly which backseat drive computer we have on this vehicle, but we often use on smaller vehicles, we use a sort of Raspberry Pi type, you know, it's just a little board. It's probably the size of the mouse. So not quite the sort of thing with the flashing lights and whirring tapes and things.
I'll get the question online here so we don't miss it.
See, there's a question when you.
Yeah, get that online one.
Okay,
Yeah.
sounds good. They just say, it's Reza says, I would appreciate if Dr. Bose answered my questions at the end of the presentation. How without a GPS input, the immersed AUV goes to the predefined waypoint? Are the back seat and front seat computers modeling the distance moved to the waypoint by considering the thruster's pitch and RPM? If yes, how accurate is it and how possible is it to lose the AUV?
Yes. I hope you can hear me. Well, it is possible to lose the AUV. I explained earlier in my talk about having a box that the vehicle control computer, it has the preset box, and we set that prior to the mission. And if it goes outside of that, the mission aborts, basically. How does it navigate without GPS? Well, when it's on the surface, it has GPS. As soon as it dives, it loses the GPS signal. This AUV now has an inertial navigation unit, and in nearly all of the missions we were doing here, we also have bottom lock, by which I mean we've got an ADCP sonar which is pointed downwards and is measuring drift against the seabed. So we weren't, even when we were offshore, our missions were not, except the shallow water mission, they're not too far from the seabed. We've got bottom lock with the seabed, we can measure drift. So through from the initial GPS on dive, the inertial navigation system is like a dead reckoning, you know, distance run and heading and all the rest of it. And you're also correcting for drift, which is your current, through the ADCP. It's not perfect. With that system, you're supposed to be 0.1% a track. Practice, it's more than that. The vehicle always, though, thinks it knows where it is. It's, you know, it's really self-confident because it thinks it knows where it is. But of course, what happens when it surfaces and the GPS comes in, you suddenly see it leap. So because it corrects for where it really is rather than where it's thought it was. Yeah.
Great. Thank you. Yes, for your question.
Just one comment. I think the lessons learned from August trials and stuff like that, and to a sampling position. I like, if you look at, the first question is, if you look at acoustic telemetry communication with the ship and the AUV, you know, for positioning, but also for correcting in position and things like that. I know that Innovacy's done a bunch of stuff like that, and others are doing with some, you know, submersible sensors. That would allow you maybe to communicate with the thing and those sorts of things. The second thing is acoustic telemetry is not global satellite connections. Perhaps I think, you know, this type of application of sampling, taking the grid and sampling different substances would have great application in fisheries and aquaculture, right? For ecosystem kind of monitoring and those sorts of things. So looking forward to those developments, in particular for our group here that's working in fisheries ecology.
Yeah, so I didn't say, but we had a USBL system on the ship, mounted over the side of the ship. We got beacons on the AUV, so that's how we know where we were getting signals back intermittently from the AUV of where it thought it was. That's how you can get that sudden jump when it rises. But that's about the only message you can get, right?
You can't give it corrective action or anything.
You know, but which is why you have to pre-think, because you can equally well send a very short message through, like go to line X in the code.
Yeah.
So that's the type of communication you can make. You can't guarantee that it hears you. Not unlike backseat drivers, basically, but you can't guarantee that it will get through. So sometimes you have to send the same message a few times, and you have to be careful when you do that. You don't override, get it to do 3 times the thing that you asked it to do. You know, so you have to be very careful how you design your code. Yeah, so that's definitely the case. But yes, there's a lot of instrumentation, a lot of equipment that I glossed over. But the type of AUV and the type of systems in use is exactly the same as a survey class Kongsberg system or even ISE brand new system. It's just that this vehicle happens to be 18 years old, which is where a lot of our problems are coming from. There's another question there.
Yes.
Oh, you also asked, yeah, absolutely. In terms of can be used for other things, the primary part of what we were testing was actually not the oil. It was actually, how do you get this thing? How can you design a more and more complicated mission and get some really, really good, useful information out? How do you, so you could put another sensor on, it's just the interface that has to change. The analysis is still the same. That's the focus of our research, basically.
You're thinking about fishery surveys and ecology.
Yes, yes. And one of my students wants to look for microplastics and yeah, so there's all kinds of things you can do.
Yep. The next question online from Nancy says, what was in the sample that was collected on the last mission, and was there any oil?
We're waiting to hear. We've sent them off for analysis. We still haven't got the results back.
Great. Crossing fingers then.
Yes. Although, be surprised if there's cross the
Be
fingers.
hopeful.
Yeah.
And then someone else online says the Raspberry is a small one regarding its computing capacity. Did you need to do a lot of work to fit your program into the Raspberry? Thank you.
That's a good question. As I said, I'm not sure, can't remember exactly what the machine is on this AUV. We've been using Raspberry Pi and others on our little AUVs, on the glider actually. Craig has been using on the glide, and Craig's working with the Seabird vehicles too, and we're thinking of that partly for the size as well. They have a surprising amount of capacity for what we're trying to do. Although the more data you've got and the more analysis you set up, obviously it's a limitation. Yeah.
Great.
So you mentioned 3,000 meter capable vehicle. know you're diving or eventually dive 600 or 700 few of those. Had you planned, and you know, on your presentation you didn't, did you plan to do any deeper than 200-meter dives, and the gremlins stopped you from doing that?
We were stopped from even getting to our. We only did one mission to 200 because we didn't want to cause the leak before, and then because every time we got the leak alarm, we had to take the thing to bits again. So that's why we did the last day mission at a shallow depth first, and then we threw everything into that last 200-meter dive. Unfortunately, with this 18-year-old vehicle, that's what we were forced into. Normally, if that vehicle was brand new, we wouldn't have that problem. So it was frustrating too, but not a lot we could do about that. Yeah.
Anyone else?
So what was the actual cause of the leak alarm?
The leak, the water in the hull was caused by a. No, we had to strip it apart, and we dropped a tiny, a piece of solder that had fallen into the.
That's on the 200. That was on the 200. Your last one. But what about previous to that? You were getting.
We were getting. I talked about the leaks on the motor, so that everything was linked. So we kept getting a water alarm, a ground fault alarm on the motor circuit. And because of the way the electronics was set up, sometimes that showed up as a direct water alert. Well, it was a ground fault basically, but we didn't know exactly where it was. So we assume a water leak. So we take the connector off, clean that out, put it back together, launched it, seemed okay. So we went off and did a mission, got it again, took it apart, seemed okay. But so we started to take the whole thing apart. There was one part of that we couldn't get apart with the equipment we had on board. And it was only after we got it here and tech services and sent the piece off to tech services, they got it apart eventually after, some time, because one of those parts was actually, there was some corrosion on it, right?
So while I have you then, with tech services, what did you decide to launch stern and not saddle over the side like a swing out over?
One of the ships that we were thinking of using, dare I say it, was the Polar Prince. The Polar Prince couldn't launch over the stern, which is a problem for this type of launch. And in the end, it cost too much anyway. So, but putting the cost aside, that we want to launch and recover over the stern, especially recover over the stern, because the ship needs to be moving ahead slowly. So you're motoring, you essentially motor the AUV up to the ramp with power on the AUV propeller. As you get close, you might actually reverse the propeller to keep the line taut. So there's someone operating. In fact, we have a belly pack as well. So Gina, with the pink helmet, was the operating the belly pack to keep that AUV, the tension in the line that's attached to the winch. So it's a combination of keeping the ship moving slightly and the AUV, because you don't want the ramp to come and clump your AUV.
But in terms of all of that, you decided to go with a stern. Did you anywhere in the design somewhere along the way, or was it too big, or what was the reason for not doing with a side launch, like in a harness?
Oh yeah, the launches with that AUV had usually just been dropped from the crane, but because we knew it was a mission that was offshore primarily, those types of launch and recovery using a crane, you need two hook-ons. You usually need a rib in the water. We didn't want to put crew in the water if we had to, so that's why we had these ramp systems are used with AUVs that usually operate offshore, and there's a variety of different designs for the ramps.
Yeah, I mean, the most dangerous part is always the retrieval or the launch is the worst, trying to get it in the water once you get it in there itself. Okay, thanks very much.
Yeah, and one of the things it's not obvious first, the AUV is actually almost neutrally buoyant. So if you just tap it, it goes down quite quickly, right? So it's not really buoyant, and it's very easy for it to get sucked into the propeller of the ship, which doesn't do either very much good.
How did you get your winch wiring connected? I mean, you had that little pop-up with the rope, so how did you actually, you hook that and then you pulled that in and somewhere there was a connector?
The two connected.
Okay.
And there was enough length to be able to wind it all onto the winch drum. Yeah. A lot of thought went into that.
Thanks, I'm sure.
Yeah.
There's just one other question on mine here that says, I'm curious about what language your team used to make the program.
Yes. Well, we worked in English. You can see the publications in English on the ship.
Oh, computer program.
I think
Oh, the computer, but on the ship they were using Greenland language. For the program we used the Moose subroutines are written in C++, and some of the other things are running in a Python, and yeah, there's a variety of stuff that different people are using.
Okay, time for one last question.
I kind of joined a little late. I was actually going to ask if you did any type of modeling to ensure like strength of the hull, like in terms of like FEA modeling and everything like that. But
the vehicles are, the AUV is a commercial AUV, so no, we didn't, but that has been done. Yeah.
I actually have a quick question. How long was the average mission? How long did it last, and what's the maximum amount of time that it could be deployed?
The longest mission we did there was that zigzag, which was about 2.5 hours.
Okay.
It's nail biting 2.5
I
hours.
can imagine.
But we had it in the water. We did that mission, and we kept going to a second mission. So the batteries on board now of that vehicle were about I think a total of about 16-20 hours of mission time. We never ran over 8, but so each time we pulled it back, we went into recharge. Yeah.
Great. Great. Well, thank you so much. Thanks to everybody who attended in person and online, and thank you for your presentation. I have a little gift here
Well,
from the
thank
Marine
you.
Institute Graduate Society.
And thank you very much for the invitation and for coming and listening.
Yeah, that's great. Thank you.
I'll put in a self-plug for Dr. Bose and Money Explorer. On July 18th, we'll have an alumni day in Holyrood at launch, open house to anything. The vehicle hopefully will be on display
Thanks.
during that time. So July 18th, come along.
Great.
You got time for more questions?
For sure. Yeah. For about a few minutes. Yeah. But is there anyone wanting to come in? That's the other.